Hi, so this will be part of the series where I go over problems from my Biochemistry I workshop at UT Dallas that I have not finished in workshop. I think it'll give students a better idea of how to go through these problems without me being there. And if you're not part of UT Dallas Biochemistry, I have the problem here. I'll try my best to show it at all times, and so you guys can try it out as well. But this one is specifically dealing with pH and different kinds of chromatographies and pKa and how they kind of relate. So we're given this huge paragraph. Let me try to zoom in. Okay, so here, oops, okay. So here we're talking about mammalian IgG antibodies, okay? And they're basically used as medical treatments for disease, targeting different diseases, okay? And kind of just talks about their origin, how they're kind of derived, and then basically skipping all of the minute details, we are basically going through the process of isolating and purifying IgG from serum, okay? So it basically, this whole process is isolating this antibody from serum. So we basically go through, first it says we go through chromatography using protein A to protein G matrix, which binds to the Fc region of the antibody, and then we pass it through this column, this protein G column, and then we wash it off with PBS, and then we put in this sodium acetate, which has a lower pH than PBS and serum, and collect it and expose it to base. So I'm going to kind of, that's a lot of words. When I first went over this problem, it was kind of hard to imagine all of this happening, but I think it's pretty vital to kind of visually imagine this so that you can be successful at this problem. So let me try to take you step by step. Okay, so here's what we're basically doing. So first it says that we are, so basically we start at serum, okay? So this right here is serum. And serum has a bunch of different kinds of proteins and other molecules. And but we're kind of focused in and targeting one specific antibody, which is IgG. Okay, so let's say serum has this sort of thing. It has circles, it has squares, but what we're interested in is this black triangle. That's what we want to, I'm making it black because that's what we want to target. That's our target. That's IgG antibody, okay? So, first, we perform a chromatography using protein A or protein G matrix, which binds to the Fc region of the antibody, okay? So we can already start looking at D after I draw this. So we basically have this column, and in this column we have these proteins. Okay, and these are basically the binding sites. I should have just not blocked it off, but these are basically the binding sites for the specific antibody. And it binds to the Fc region, so let's say this is the Fc region of the antibody. So we basically put in all of these things through the serum, but the protein G matrix, will only bind to this, okay? So everything else will be kind of falling out of the serum except for this. So what kind of chromatography would this be? You have a protein that specifically is binding via a specific site on the Fc part of the antibody. So think about what kind of chromatography that may be. Let's just say there's a lot of affinity between the protein and the antibody, okay? All right, so that's D. So we're basically done with that. Now continuing this whole process. So we're basically going to collect all the stuff that we don't need in this first beaker, okay? We're basically going to collect that, and then we're going to take that beaker and put it aside. All right. So, moving on, we then wash it with PBS. Oh, by the way, I should mention, the serum pH this will come in use later, is around 7.4 physiological pH. And then we put in, after we put in the serum, and then we wash it out with PBS. And PBS is a pH of, I believe, 7.9. Yes, 7.95. That's the pH of PBS. And so PBS, in case there's like a square left somewhere here or a circle left somewhere there, it'll wash it out. So PBS will wash this out in case there's anything stuck in there. So we'll still collect it in that same beaker that we had initially. Okay, then what we do, then what we do is we then we elute it with, and elute the, by elute, it means separate the IgG. So now we're going to take that IgG, the black triangles that binded to the proteins, we're going to elute that out of the column using Na acetate, pH of 3. Okay, so notice how the pH of Na acetate, sodium acetate, is a lot lower than the other two materials that we used. Okay, so and this will be another beaker, and in this beaker we'll actually have tris base. So this is tris base, and it gives the pKa and all that fancy stuff about the tris base. But then basically the black triangles will fall out here, and we'll have successfully isolated the IgG antibodies from all the other stuff in the serum. Okay, so that's the process. I know that's kind of lengthy, but now you guys understand what we're basically doing in this problem. Okay, so now we can actually start solving the problem. Okay, so the first one, what are the concentrations of acetic acid and acetate in 0.05 molar sodium acetate? pH of 3 is used for the elution of IgG. So instead of using 0.05 molar, I'm going to use 0.07 molar, just to slightly change the problem up so you guys can do this later on your own. So what you have to kind of notice here is that that acetic acid is a weak acid. So whenever you have a weak acid, that's the acid, and when you add it to water and the acid dissociates, it will make protons and the conjugate base. Okay, but notice this reversible arrow. That means that it can go this way, but then some of the conjugate base may then revert back into the original acid. So you basically have reactions going both ways. So just because you have 0.05 sodium acetate doesn't mean you won't have acetic acid. Sodium acetate would be the conjugate base in this scenario, and acetic acid would be the original acid. Okay? And so hence we'll have concentrations of both eventually. If we start with this, some of it will go this way, some of it will go back that way, so you'll end up with concentrations of both. And so that is basically a mixture. And whenever you have a mixture, your mind should think Henderson-Hasselbalch, okay? So you have a pH, this is the formula for Henderson-Hasselbalch. You have pH equals pKa plus log of the conjugate base over the concentration of the original acid. Okay? So essentially, this right here is acetate, and this right here is acetic acid. Okay? Now, here's the kind of tricky part, that we don't know we have two unknowns here. We don't know this, and we don't know this. We know the pKa, it's given in the problem, and we know the pH, it's given in the problem, but we do not know the concentrations of each of these. All we know is that we start off, that the concentrations of both of these will be equal to 0.07 molar. Why? Because even though this should be 0.07. Why? Because we start off with sodium acetate. We put in all of the 0.07 molar as this. Some of it will convert, and some of it will reconvert, and blah blah blah. But essentially, you'll have these two concentrations adding up to 0.07. Make sense? So that's why they'll be equal to 0.07. So what we can do is we can convert one of these to the same variable, and here's how. So it'll make sense in a second, I promise. So you have pH equals pKa plus log, and I have acetate on top, the acetate concentration. Now you know acetate plus acetic acid is 0.07, so acetic acid then is essentially 0.07 minus acetate. So acetic acid is basically 0.07 minus acetate. So see what I did? I have the same variable now. I just have one variable to solve. Okay? So then I plug in my numbers. 3.0 is equal to the pKa given is 4.76 plus the log of, I guess you can make it x. X will be acetate concentration, keep that in mind, over 0.07 minus x. You're gonna solve for x using algebra. I'm not gonna go into the nitty-gritty details, but essentially I get x, which is equal to the concentration of acetate, is equal to 1.24 millimolar. Okay. Now, how do I get acetic acid? Well, I know that acetate and acetic acid, when they're added together, they make 0.07. So, acetic acid concentration would just be 0.07 minus the acetate concentration. Okay? And so it would be 0.07 minus 0.00124. And for that, I get 68.8 millimolar. So this is my answer for A. Long problem. Alright, and it's already been 13 minutes, so this video will probably stretch kind of long. But we're almost there. Alright, halfway through. Now we have B. Okay, so let's look at B. What is the final pH of the 1 milliliter fractions containing purified IgG? Final pH of the 1 milliliter fractions containing purified IgG. Okay, so essentially now we're at this point where we have eluted out these black triangles, the IgG. We've eluted these out, and now we're going to find the pH once we've put it into this 1 milliliter sample of the base. Okay, this one's kind of trickier than the first one. So let's kind of look at how we're going to approach this. Oops. I don't know how to undo yet. I'm still learning this program. Alright, so I'm going to make this black. Okay. Alright, so we're in this we essentially have when we dump out that black triangle, when we dump out these black triangles, it's not just the black triangles that's going through. It's also the acetic acid that's going through, right? The acetic acid. So whenever we kind of dump in the second elution, after we've done the PBS in the second beaker, when we put that sodium acetate in at a pH of 3, we'll have, then going into the base, we'll have sodium acetate / acetic acid. We'll have these IgG antibodies, and in this container we'll have tris base. So all three of those components will be at play here. Okay? So let's keep that in mind. So you have an acid, you have a base. Sounds like it might be an acid-base problem. Okay? So, one thing that you should notice is we have acetic acid, we have tris base. Acetic acid has a pKa of 4.76, and tris base has a pKa of 8.1. What does that tell you? What does that tell you about where the protons will go? Well, you know that a higher pKa means a lower Ka, which means it's a weaker acid / better base. That means that this is a better base and this is a better acid. So the protons will be donated this way. Okay. So now writing the reaction. It's just an acid-base reaction. You have the acid, you have the base, and the acid will donate its proton, creating water and the conjugate base. Now water does not matter in this equilibrium reaction. What is the initial concentration of the acid? What is the initial concentration of the base? And what is the initial concentration of the acetic acid? We actually have, of the conjugate base. We actually have all these values, okay? We actually do. So one thing that you want to really take care of here is account for that 1 milliliter fraction that you see. You see in the problem it says containing 1 milliliter fractions into tubes containing 45 microliters of 1 molar tris base. So you really want to take care of that. So let's do the tris base first, since I believe that one's the easiest. So it says 45 microliters of 1 molar tris base. All right. So I'm going to have a separate calculation placed for this. So for the tris base, you have 45 microliters. So 45 times 10 to the negative 6th liters. You have 1 molar, and you essentially want to get moles. Okay, we want to get moles. That's our goal here. So you know that molarity is moles over liters. So you just do 1 divided by, you have 1, and you want to find moles, and you have the liters. So then you know that cross multiplying these two, moles is exactly the same thing. So here in the base you have 45 times 10 to the negative 6 moles. Now just to kind of cut time, because it's almost a 20-minute video, I'm going to write down the moles of both this acid and the conjugate base. And now you guys can calculate this yourselves. We have the moles. Convert this to moles. It's in millimoles right now. And we have the liters, right? The liters will be 1 times 10 to the negative 3 liters, because we have milliliters here, 1 milliliter. So then you find the moles of each of these. So then you'll get 2 answers, and let me just write them down for you. Here you'll get 6.88 times 10 to the negative 5 moles, and here you'll get 1.24 times 10 to the negative 6th moles. Water does not matter. That's our initial concentration. Okay? Now what's happening? The acid is going to react with the base and form the product. Okay? And how much of it will react? Well, the base will be completely used up. Whichever one is in less quantity will be completely used up in the reaction. In this case, we have less base. So the reaction will proceed this way until you have run out of base. So you have minus x, plus x, but we already know what x is here. X here is 45 times 10 to the negative 6th. So here you have 6.88 times 10 to the negative 5 minus 45 times 10 to the negative 6th. Here will be 0. and here will be 1.24 times 10 to the negative 6th minus 45 times 10 to the negative 6th. Okay, so for my final values then, I'll get 2.38 times 10 to the negative 5 moles, I'll get 0 moles, and I'll get 4.624 times 10 to the negative 5 moles. Okay, good. Almost there. We're almost there, guys. All right, so what are we trying to find again? I mean, we're kind of lost, right, after going through all of this. What is the final pH? All right, so we have certain concentrations of the acid. We have certain concentrations of the conjugate base. We know the pH. No, sorry, we know the pKa, right? So then we can calculate the pH. So the pH, it's a mixture, right? You have both. So pKa plus log of these two quantities. The conjugate base on top, the original acid on the bottom. Now, it doesn't matter if this is molarity. It doesn't matter if these two are millimolars or millimoles or moles. As long as they're the same units, it's just a ratio. So it doesn't really matter. So we can keep these as moles. We don't have to reconvert it to molarity. Okay? So all you do is you put in the pKa. Which one would you use here? It would be the 4.76 because it's the pKa, basically the acetic acid is the one losing the proton. So it'd be acetic acid's pKa, and then you would put in these two quantities. And for my final answer, the pH, I got 5.05. All right, I'm going to take just 2 more minutes and go over C. All right, so why do we do all of this is essentially what C is asking. That's what it's asking, and we've already kind of gone through most of it. So what's really happening here? When we have the serum and when we have the PBS, these are both very, very basic pHs. Now, you guys might have learned this in lecture or will, but you guys will know that we have proteins, right? And proteins are made of amino acids, and amino acids have carboxylic side chains and carboxylic main groups. These carboxylic side chains and carboxylic main groups, COOH. Now, the pKa of COOH is somewhere around 3. So when you go above this pKa, when the pH is above this pKa, and I'll kind of explain how the relationship between the two in another video, this proton kind of goes away. It leaves. It's deprotonated. And that causes this to be a negative. So what was happening was essentially in these two liquids, serum and PBS, we had a really high pH. And so we had a lot of this going on in both the protein and in the antibody. In the protein and in the antibody. And so that basically allowed for charge interactions, which allowed for this specificity, which allowed for that Fc binding or whatever it was between the IgG antibody and the protein. But once we put the sodium acetate in, so after we got rid of all the other stuff, once we put the sodium acetate in, then we had a really, really acidic pH. We had a pH of 3, actually. So some of these were then they were reprotonated, causing COOH, and that charge interaction between the antibody and the protein was lost, and then these proteins then fell out. Now, the reason that they fell out was because these became deformed. These triangles, they became deformed into like this kind of a shape, and so they couldn't fit into that region in the protein anymore, and so that's why they fell out. But then finally, why do we have the base at the end? Remember, the base has a really, really high pH, and we're interested in the original antibody. So what it'll do is it'll reshape, reform, and restabilize these antibodies so that they'll resume their original triangular shape. So that is this problem, C. Let me zoom out so you guys see all of it. No pun intended. Okay, I'm going to leave it here for just 10 seconds. So thank you so much for joining me on this video. I'll try to keep them shorter in the future. I know it's like 25 minutes. I just want to make sure that you guys get the same quality of teaching without me actually being there. And for those online who are not part of my workshop, I hope you guys enjoyed this challenge as well. So I'll see you guys next time.